All right, this is going on page 99 when we're done. So in this section, we will explore several ways to write equivalent representations of trigonometric expressions. That means we are changing the way it looks. We are not changing the value. We are changing 2/4 to 1/2. We are changing the square root of 12 to 2 square roots of 3, right? It's equivalent representations. So we have to know trig identities. The good news is all of these right here, you really already know. And because I'm not a big fan of the word memorize, we have to learn them and know them. And these, I think by now we've learned and known. If I just told you right now, that'd be a whole different story. But we know that sine, what is sine the reciprocal of? Cosecant, right? There's got to be a co in each pair. So this sine of x is the same as 1 over cosecant x, which means cosecant x is the same as 1 over sine x, like it works both ways. Right? Cosine is the reciprocal of what? Secant. So this would be 1 over secant x, and secant is the same as 1 over cosine x. Everybody good with that? Tangent is 1 over what? Cotangent. And we also know another rule for tangent. Tangent is also what over what? Sine over cosine. So tangent x I can also write as sine over cosine. We learned that day one when we did the unit circle. Cotangent x then we can write as 1 over tangent x. Or since cotangent is the reciprocal of tangent, I can take the reciprocal of this one and get cosine x over sine x. So we already know a huge bulk of the identities, and they're called identities because they have the same value. You can substitute them in for each other, all right? Everybody good so far? Like old news, right? We got that down. Hopefully we got that down. Okay, so these identities will allow us to manipulate trigonometric expressions and rewrite them in equivalent forms. Equivalent forms, that's a terminology that has come up a lot for us. All right. So we will start by, it says let f of x equal this fraction. Then it tells me to rewrite f of x as an expression involving tangent of x and no other trigonometric functions. So I can only have tangent x in there. It could be tangent squared. It could be 2 times tangent, but like tangent can be the only trig function in there. So the good news is you kind of know your goal. I don't know my exact answer, but I know what my answer is supposed to look like because we could rewrite this in all kinds of things, right? I could make 1/2 2/4 or 4/8 or 5/10 or, there's like an infinite amount of things. So I have some sort of goal there. So let's start by just rewriting just the expression part here. So sine of x times secant squared x over cosecant x. So when you're dealing with trig identities and you're manipulating these, there's a lot, of course, you don't know all of them yet, but there's a lot of things I could substitute in here. But you have to have some sort of plan as you go in, like what would make the most sense here? Well, if I'm trying to get to tangent, I either need to get to cotangent, which where you are right now, you don't necessarily look at this and go, oh, I see how cotangent is, related to that. And I wouldn't expect you to. But I do know that tangent can be sine over cosine. And I feel like I could get this into sine over cosine. Okay, so that's one strategy is to change everything to sine and cosine. It's not always the best strategy, but it is one of them. And you don't always know what the best is when you start. That's why you kind of think through things before you just jump in. But right now, that's kind of the only thing we got. So that's what we're going to do. But before we do that, I'm going to rewrite this a little bit just to help you make sense of it. And I've got sine of x times secant squared x times 1 over cosecant x. And I want you to look at that and understand how that is the same thing. I just it's not really splitting the fraction. Splitting the fraction is a different thing. But like I made it not in one fraction, right? If I multiplied it all back together, I'd get this. You agree with that? And that way we see them separately and we don't do anything weird with the denominator stuff because that's what happens sometimes. All right, so if I'm trying to get to tangent and I'm thinking, okay, I'm going to try and do everything in terms of sine and cosine. Sine of x is totally fine just like it is. So sine of x is sine of x. All right, then I have secant squared. What is secant the reciprocal of? Cosine. So if I have secant squared x, I can change that to 1 over cosine squared x. So even when they're squared, we can take the reciprocals. As long as there's no addition or subtraction, it's totally legal. And then I have 1 over cosecant. What's another way to write 1 over cosecant? Sine. Okay, so then I have sine of x. Everybody okay so far with where everything came from? Yes? All right, so now I'm going to multiply all that back together. If you want to put these over 1, that helps you to actually see it. I think sometimes some of you need to see that so you don't do weird things. Some of you would still do it fine if you didn't write that. It's up to you, whatever works for you. But when I do this, I'm going to multiply straight across. So in the numerator, I'm going to get sine times sine, which is sine squared. In the denominator, that is cosine squared. Are y'all laughing at me? Because if you're laughing at me, you need to have enough respect to say it to my face so I can laugh too. No? Okay. What is it? There's a spider. Okay, I'll save your lives. That's an icky spider. Oh, now he's on my shoe. There he is. Okay, a spider's not something to laugh at. A spider's something to say, hey, let's kill that spider before he eats us. Okay, I'll move him out of the way. Oh, are you watching him? Is that what you were doing? You were waiting for him to jump on me, weren't you? Okay, no, all right, whatever. All right, are we all good here? Now that I saved everybody, now I'm your hero. Okay, I got sine over cosine. What is sine over cosine? Tangent. So I can make this into tangent squared x. And then I have it just in terms of tangent, and I'm good. Full disclosure, if it wasn't something icky like a spider, I probably would have saved it and taken it outside. But I ain't about playing with spiders, so you can just stay there and be dead. All right, are we good? Are we okay with that? I've saved lots of lizards and worms and all kinds of other weird things that come in this building. All right. So let's try. Any questions about that? I know we got very distracted by the spider, but we're good. Okay, so now I have cosecant x times tangent x, and I want to rewrite it as an expression involving secant x only, no other trigonometric functions. So let's just start by rewriting this. Cosecant of x times tangent of x. Okay. All right. And again, I can substitute some stuff in here. I know I want secant, and it's not like a sine or a cosine, but what is secant the reciprocal of? Cosine. So if I can get it to cosine, I can get it to secant, right? And I feel like I could probably do that with what's here. So let's just go ahead and put everything in terms of sine and cosine and see where that gets us. So what else? How can I rewrite cosecant in terms of sine or cosine? 1 over sine. Good. So this is going to be 1 over sine of x. And then how can I rewrite tangent? Sine over cosine. Good. So sine of x over cosine x. And then do you see something I can cancel out? Yep, I can cancel these out right here. That gives me 1 over cosine x. And what is 1 over cosine x? Secant x. And we have rewritten it. So this here has the same value as this here, just a different form. And it's simplified. Okay. What questions you got? We good? All right, flip it over. Let's look at one that we haven't seen before. So here it says we can discover, and that's what we're going to do, several interesting properties and identities that arise from our understanding of the unit circle. So here is our unit circle. So I want to remind you, not every circle is a unit circle. I know this one is because first of all, it tells me, and second of all, the radius is 1. And then we know that if I have this point P, that point is cosine theta sine theta. That's old news as well, which means this is my x value, my y value, and then the radius is 1. So we know from like 6th grade that if I have a right triangle like that, I can do y squared plus x squared equals 1. You agree with that? Okay, that makes sense. That's your Pythagorean theorem. So any point xy can be expressed as cosine theta sine theta, where x is cosine theta and y is sine theta. Okay, old news. We got that down, I hope. So then we can apply the Pythagorean theorem that we just wrote down right here. And if I substitute these in for x and y, I'm going to get sine squared theta plus cosine squared theta equals 1. Okay, so for any angle, the square of the sine value plus the square of the cosine value is going to give you 1 every single time because of the Pythagorean theorem. This is called the Pythagorean identity. Okay? And that's one that you just have to know. Okay? Whether you want to call it memorizing or whatever you want to call it, but you got to know that one. If you know that one, you can get to all the other ones that we need to know that are Pythagorean-like. And I'm going to show you how right here. So we're going to start with sine squared theta. Let's just write this down. Read my handwriting. Sine squared theta plus cosine squared theta equals 1. Okay. Now that might be the only form of that particular one that is shown to you on a formula chart, which is fine. Okay, but I could rewrite this as sine squared theta equals 1 minus cosine squared theta. So that's not a huge leap, right? I just solved for sine, just moved cosine over, right? So depending on what I need to substitute in for, maybe this form is better. Or maybe I need cosine squared theta equals 1 minus sine squared theta. Right. But all three of these are basically the same, just kind of rearranged, right? So if I know this one, those two are not a huge leap, right? There's no reason to like know all three of them. If you know this one, maybe you just in your brain you can get the other two, or maybe you need to write them down, whatever, but it doesn't have to be like a brand new equation. Then there's other forms, but they're all going to come from this orange one right here. So let's rewrite this orange one. We've got sine squared theta plus cosine squared theta equals 1. Okay, so then I'm going to take this one and I'm going to divide every single term by sine squared theta. Okay, every single term is going to get divided by sine. I just picked the first one, divided all three by that. So sine squared divided by sine squared is 1. What's cosine over sine? Cotangent, right? So this is going to be plus cotangent squared theta equals, and then what's 1 over sine? Cosecant. Cosecant squared theta. So there's a Pythagorean identity with cotangent and cosecant in it. Again, here, most formula charts would probably just have this one, but I could have 1 equals cosecant squared theta minus cotangent squared theta. Or maybe I have cotangent squared theta equals cosecant squared theta minus 1. And that's just by rearranging this one right here. And I keep making reference to formula charts. Let me make this very clear. You do not get one on the AP exam. That is why you have to either know these or know how to get them easily, all right? And I think that knowing how to get them easily is really probably what most people need. I know some of you may have little brains that just kind of know these things once you see them. That's not how most people's brains work. Now, I pretty much just know them, but I've been doing them like forever. You've been doing them for about 10 minutes. So, you know, and you won't have been doing them that long when you get to your exam either. So, I mean, you can try and memorize them if you want, if that's the way your brain works, but otherwise, I want to make sure you know how to get there. All right. And so then we have, let's do one more. So let's write down our orange one again. Sine squared theta plus cosine squared theta equals 1. This time I'm going to divide everything by cosine. Divide each one of these by cosine squared theta. So what is sine over cosine? Tangent. So this is going to give me tangent squared theta plus cosine over cosine is 1. And then what is 1 over cosine? Secant. I've got secant squared theta. Then I can rearrange this a little bit, and I can end up with tangent squared theta equals secant squared theta minus 1. Or I can have 1 equals secant squared theta minus tangent squared theta. But, you know, I can at least get to that one. I can manipulate the rest. So remember, it's all about knowing this one, being able to get those other, by just knowing what's in orange right there, you can get everything else that's on here, right? And you might only need one of these others on the entire test. So it's not like you have to redo it 1,000 times on the test or anything like that. But there's no telling what they could actually ask you for. So the actual identities here then that we have, the equivalent forms here, let's write down sine squared theta plus cosine squared theta equals 1. This is the guy that you absolutely have to know. Okay. Then we have 1 plus cotangent squared theta equals cosecant squared theta, and tangent squared theta plus 1 equals secant squared theta. All right, so if you are interested in trying to commit those to memory, let me kind of give you a little way that you can put all the pieces together and kind of what goes on in my brain. First of all, we have 1 plus cotangent squared. Couldn't I put cotangent squared plus 1? Would that be the same thing? Yeah, I wrote them out like this because that's how you would see them on a formula chart if you ever use them like in the future when you go to calculus and you need this stuff. Like that's probably how you would see it if you looked it up. But if you look at this, now we know when we pair up reciprocals that there has to be 1 co in every pair, right? So we still just have to know this one. But when we get to the identities here with the reciprocals in them, the co's go together and the non-co's go together, right? And it's the tangent and the cotangent that's plus 1, and it's equal to the secants or the cosecants. Okay, and you can kind of see patterns and things. It helps you kind of put the pieces together. But again, worst case scenario, you write this down and you go, okay, I need to get to something with a cotangent in it. Well, if I need cotangent, I need cosine over sine. So that means I divide everything by sine and it would get you here. Okay, we're good with that? Kind of see how that works? All right, so let's do an example. We've got the function f is given by tangent over cosecant. We're going to rewrite it, and it tells me I'm going to have a fraction involving powers of cosine and no other trigonometric functions. So I know my answer should be a fraction in the end, and I should have cosines and nothing else. So I'm going to start off then with, again, we'll just go ahead and change everything to sine and cosine. So let's just rewrite what we have first. Tangent of x over cosecant x. Okay. So I know I can rewrite tangent as what? Sine over cosine. So I'm going to make that sine of x over cosine x, and then a big old fraction bar. And I can rewrite cosecant as 1 over what? sine. Okay. Now, I have a fraction and a fraction. First of all, I'm not going to freak out. Second of all, I'm not going to make up math, and I'm not going to take any shortcuts and do something ridiculous. I know that this right here just represents a division sign. So I'm going to do my fraction rules. I'm going to keep the first part, so sine x over cosine x. I'm going to change division to multiplication, and then I'm going to take the reciprocal of the denominator, which makes that sine of x over 1. Because you might be kind of tempted to cancel the signs out there, but you cannot do that. That's not the way it works. Right? So then we multiply straight across, and that's going to give me sine squared x over cosine x. All right, well, I got a cosine in there. Remember, it says cosine and only cosine. And I know you have stuff up at the top of your paper, but pretend like it's not there, okay? If you've got a sine squared that you need to get rid of, then you want to think about your Pythagorean identity, which means I'm going to think about my sine squared theta plus cosine squared theta equals 1, right? I'm going to use that. And I need to substitute, I need to get rid of the sine squared. So if I solve this for sine squared, that gives me sine squared theta equals 1 minus cosine squared theta. So now in my little fraction that I'm supposed to have a fraction that's supposed to be only cosines, if I replace sine squared with 1 minus cosine squared, I get 1 minus cosine squared x over cosine x, and I'm done. Could I manipulate it more and simplify it more? Yes, I could. And we're not going to do that today. I'll show you that when we come back to it. But I don't want to because I did what it said to do. I have cosines in there. It's in a fraction. I'm done. Okay? We good so far? Any questions? This is totally doable. They're like little puzzles. All right?